Okay, good afternoon. We'll go ahead and get started with some announcements. Your exam 0 is now graded. You should be able to see that in zip grade. Those scores are not going to be transferred into Canvas until the end of this semester, where I'll sum up all of your module exam scores and then put them in one column. So if you want to track your progress, you can download the Excel file that's in the syllabus and keep track of your points that way. Module 1 exam is next week, Wednesday. So again, it'll be through zip grade. Normal deal, 30 questions. Anything after that is a bonus for that. I'll mention it now, even though it's a couple months away. The final exam in this class is not only for 256, it's cumulative for 255 and 256. So it carries a pretty beefy percentage of your total letter grade. Look at the syllabus for how the points break down. So you might want to consider buying this. It's not required, so you have to pay out of pocket for it. And they sell it, Diane sells it up in Tech for $30. I think it's $28 now. Maybe it's $31 due to inflation and tariffs, I don't know. Or you can buy it online and have it shipped to you. This is the old version. The new version is orange, and it breaks up the content into Organic 1 and Organic 2. Any questions before we get going? So today's lecture is on aromaticity and what are aromatic compounds. And the remaining part of this module we're going to look at after we understand what an aromatic compound is, what are the reactions. And so I have up here benzene. So benzene is C6H6. There's 4 degrees of unsaturation. So 1 ring plus 3 pi bonds. So benzene is kind of weird in the sense that the way it's drawn, it looks like there's 3 discrete pi bonds. And what we've seen from Module 5 in Organic 1 and then from these lectures in 256 are addition reactions to pi bonds, where the electrophile, that reagent AB, is adding the elements of A and B to the pi bond. So aromatic compounds do not undergo that type of addition. So the definition of aromaticity means there's a special stability. And so we'll try to understand that today and why these pi bonds, as they're drawn, do not behave the same way as a normal alkene. So I say cyclohexo-1,3,5-triene. So if you imagine cyclohexane and you just shove 3 pi bonds in there, this could be a theoretical molecule where the pi bonds behave as normal alkenes. But as we'll see with the ring in the conjugated pi bonds, they do not react like normal alkenes. So there's this special property, and it's called aromaticity. So you're used to probably thinking about something that's aromatic as something that's fragrant. You can smell it. So it has this vapor pressure. You can, smell it with your nose. That's another perception. We talked about color. Smell is a perception. The little individual molecules make their way into your nose. They react with these enzymatic receptors and trigger this process. And then your brain interprets it some way. So outside of sort of a general definition of smell in terms of being aromaticity, what's the chemical definition of that? So benzene is not, that's the important part, it's not a conjugated triene. So as drawn, the double bonds do not alternate between pi bond, sigma bond, pi bond. So due to resonance, as you see in the figure here, it's kind of subtle, but what's happening from the left to the right, those pi bonds are shifting. As a consequence, every carbon-carbon bond in the molecule has the same distance. We remember that sigma bonds are longer than pi bonds, right? So if this structure existed, you'd expect that bond, these sigma bonds, to be longer, and it wouldn't have like the symmetry that's shown. But due to resonance, every bond in the molecule has the same bond distance. So that distance is 1.39 angstroms. So angstroms is defined as 10 to the 10 meters, 10 to the minus 10 meters. So we know that there's this special property present if we look at this heat of hydrogenation experiment. And so cyclohexane is the molecule that would be produced by hydrogenating the structures sort of above that bolded black line. So if you took cyclohexene and you added one equivalent of H2, that would reduce that pi bond. And you could measure the heat that was put out from that as negative 120 kilojoules per mole. So if you just shoved another double bond in there to get one cyclohexa 1,3-diene, you would expect to see, so negative 120 times 2, you'd expect to see that amount of heat evolved. So it's around there, but it's a little lower. Yep.
When you wrote down plus H2, what's that referring to?
One equivalent. So this would take two equivalents, and it's getting you to the same compound. That's why you can compare these numbers. Now, you would think that with this theoretical molecule, if we were just considering those alkenes as a conjugated system, negative 120 times 3, you would think that it would evolve that much heat, negative 360 kilojoules per mole. That would be the linear projection with three equivalents of hydrogen. Well, it turns out when you take benzene and you hydrogenate it, it's only evolving negative 208 kilojoules per mole. So there's a pretty significant difference between what you would expect by theory and what you observe. And this difference in energy is attributed to aromaticity. So it's a special stabilization that's in part due to conjugation. So there's an experimental way of showing there's a difference. And then we're going to look at some sort of mental constructs. We'll look at some diagrams about how electrons are placed into orbitals to understand a more theoretical way of what aromaticity means. How did that bonding pattern with conjugation inside of a ring lead to aromaticity? So a couple things in terms of looking at a compound or functional group and determining if it's aromaticity, if it's aromatic. Number one, there has to be a ring. Number two, there has to be pi bonds. Number three, they have to be conjugated. So those are some general visual things you can look at. But then we're going to dig a little bit deeper and further look at how electrons are placed into the orbitals. And that will ultimately tell us, is this aromatic, non-aromatic, or anti-aromatic? So I want to highlight that and just draw a pi bond plus the electrophile AB. And again, we learned that the electrophile will add across that pi bond such that each carbon gets either A or B. So that's an electrophilic addition. So benzene rings do not undergo that same reaction. Instead, they undergo a different mechanism called electrophilic aromatic substitution. So we saw benzene was C6H6. So all the hydrogens are the same on benzene. So what we're doing is substituting a hydrogen for some atom of that electrophile. So this is EAS. So a hydrogen's been substituted for some other functional group, substitution. The reason there's a difference from this case right here, what happens in this product is you're losing the stabilization due to aromaticity because you no longer have that conjugated system. When you do electrophilic aromatic substitution, the ring still ends up as being an aromatic ring. And you're not giving up the stabilization due to the conjugation part. So we'll learn those reactions starting Wednesday and next week as well. How do you substitute H on a benzene ring into something else? And then once that something else is there, can you do more reactions on it? So everything we've learned, so far about resonance is really going to come into play. Are things electron donating? Are they electron withdrawing? So you'll need to keep that in your mind as we study these reactions. So we know that a pi bond consists of two p orbitals that overlap on both of the lobes of that dumbbell shape. So you have 3 pi bonds, so that's 6 p orbitals. And essentially what happens is instead of having these sort of isolated, see how these are isolated? I said all the bond lengths are the same, so the pi cloud sort of exists as the buns of a hamburger. So you have a top bun and a bottom bun. And the electrons are delocalized over those entire faces. They're not between, any two carbon atoms. So that arises because of the p orbital overlap. And conjugation. So we have 6 p orbitals. And these p orbitals will mathematically combine to form 6 molecular orbitals. Remember from our brief discussion of going from ethene to 1,3-butadiene, we were adding these alkenes, and we talked about the number of molecular orbitals for pi bond. So ethene had 2, a bonding and antibonding. When we got to 1,3-butadiene, now there were 4 molecular orbitals. 2 were bonding, 2 were antibonding, and then you had that gap between them. So we're doing the same exercise, but now the pi bonds are in a ring. So the hybrid orbitals basically hybridize in a certain sense. We call it a molecular orbital. That just means the orbital it's not located over, say, 2 specific atoms of a bond, but basically the entire molecule. So these are molecular orbitals. So we have 6 isolated p orbitals that form 3 pi bonds. And we have to conserve them. So we're going to form 3 bonding orbitals. And 3 antibonding. So those are pi star. The little asterisk means antibonding. So these are the lowest unoccupied molecular orbitals. They'll have no electrons in them. The bonding are the highest occupied molecular orbitals, so they'll have electrons in them. As we learn the mechanism, because the highest occupied molecular orbitals contain electrons, benzene will react as a nucleophile. So it will attack an electrophile, which is electron deficient. So I have this question here, what do they look like? You'd never picture these things in your mind. Again, when you see them, they're the result of some complex mathematical equations. So that's not part of this course. That's more physical chemistry, where you learn about the Schrodinger equation. Has anyone heard of that? So you need to take calculus and all that to understand the Schrodinger equation to begin with. But what falls out of all that math are these shapes. The colors that you see are just the changes in phase. So here are our 6 p orbitals. And we're just going to mathematically combine them into molecular orbitals. And the line that you see, that dotted line moving across, notice there's nothing on there. If there was something on there, these would be called non-bonding orbitals. And then according to the energy chart, the highest occupied molecular orbitals are lower in energy. Then you get the non-bonding, and then the anti-bonding, which is, normally this, again, would have these stars here. So you take your 6 p orbital electrons, you start shoving them in there to the lowest orbital first. So that's psi1, you put 2 in, you spin pair them. Then psi2 and 3, you put the remaining 4. And since there's only 6 electrons to start with, notice that there's no electrons in these anti-bonding orbitals. And so this is how we're further going to understand the chemical meaning of aromaticity. There are certain rules that we have to meet according to plugging the electrons into these orbitals. So The first orbital has no nodes. Notice the surface on the top and the bottom. It's like a smooth surface. Like I said, it looks like a hamburger bun. There's no disruption in the location of the electrons. But when you get to CHE2, you have that split in the middle. So it looks like maybe your ciabatta bun you've sliced in half. So where there's no, or where there's space, where they don't connect, that's called a node. And so the number of nodes is the wave function minus 1. So wave function 2 minus 1, you have 1 node. And that's a region where there's no electron density. And we use that to help us predict, okay, where on this molecule can a substitution occur? So you'll see in CHE3, now you have 2 nodes. You're sort of splitting in one dimension and then orthogonal to the next. And so on and so forth into the antibonding. So this is just to give you an idea of how these orbitals look. But really what we're going to do is use a learning tool called the Frost circle to help us determine where do we place these electrons. It's pretty straightforward on how to do that, and then shove the electrons in and see what orbitals they reside in. Any questions? So a couple more compounds. What's aromatic before we get into the Frost argument? So the ones that you see here are PAHs. So polycyclic aromatic hydrocarbons. And this slide shows you linear. All we're doing is taking benzene and we're just going to append another benzene to it. And then the name you see is the special name for that. So naphthalene. Does anyone know what naphthalene is used for? So yeah, it's in mothballs. So if you know what a mothball smells like, it's aromatic, right? I mean, you could smell it from a couple feet away. So people used to stick that in their closet to keep the moths from eating their clothes. Or if you were really rich, even richer today, you might have a cedar wood lined closet. That helps keep bugs out, gives your clothes a little bit of a nice foresty flavor to them. Anthracene, you're plugging another ring on there. You might even use anthracene in one of your labs, the Diels-Alder lab. You'll do a Diels-Alder cycloaddition with anthracene, maybe, to check the notebook. Tetracene, so that's 4, pentacene, hexacene, decacene. What's interesting about these, and people study these, so if you could hold benzene sort of in your hand and you tried to move it, it'd be pretty stiff. But by the time you get here, if you were holding that end and that end, you could sort of wobble it like a wave. And so people will take one end and try to belt it to the other to make a cavity or a belt, a circle. And then what's interesting about that is, okay, I have this hoop. Can I shove something into the hoop? And so a Nobel Prize was awarded for stuff like that a couple years ago, and that's the foundation of molecular machines. So you can put functional groups on here, and then if you have a hoop, you can sort of change the pH. That'll drive things in or out of the hoop, and that motion is work. And so that's the basis of molecular machines. And if you're really into it based on the functional groups and you play with the pH, you can make like logic circuits that move things from here to here or a certain distance. So angular PAHs. Now, instead of continuing in a line, you're going to break off and take an angle. So phenanthrene, benzo C-phenanthrene, tetraphene, and chrysene. And I think with this one, you can eventually loop this back onto itself. But if you keep looping this, but you don't connect it to the start, basically what happens, these rings can't occupy the same plane. So they'll start to curve. And then when it curves, it forms a helix or a screw. And we'll talk about helical chirality in Module 5 when we talk about DNA. So we know DNA is a double helix, and it has a certain type of turn. Does anyone know what turn that is? If you go to Lowe's and you buy a pack of screws, you have a screwdriver, how are you turning your hand? So you're turning it this way. That's the way DNA turns. So that screw has chirality, like a normal screw, but the chirality of the enantiomeric screw, you would use your left hand to drive it forward. So you do righty-tighty, right? Right goes in, and then when you reverse, it's coming out. But if you had the enantiomeric screw, you would use your left hand to drive it in, and then you would drive it out the opposite way. So when you start adding those rings, you can get a certain chirality, and those are called helicenes. So one application of these polycyclic aromatic compounds, as you start to add more rings to that benzene, and you're building them out either linear or angular structure, they tend to be carcinogenic. And the reason for that is I introduced that benzene only goes electrophilic aromatic substitution of hydrogen. But the more rings you put on, the more double bonds you're adding, it lowers that energy gap. And so that energy gap can get so low that these start behaving as normal alkenes. So they'll do the addition reactions like an alkene. So these are three compounds that are found in soot. And soot's the black residue that's left over when you burn like a candle or a fire. If you burn candles in your dorm or house or apartment or whatever, and if you're a good homeowner and you check your air filter, at the end of the 3 months when you check that air filter will be black, and it's from the candles. So all that stuff you don't see, it's collecting in your HEPA filter. That's the soot. So these compounds were found out to be carcinogenic based on an example of chimney sweeps, and I'll talk about that on the next slide. It says, the regulations are written in blood. So anytime there's a rule or a law, it's usually there for a reason. And so why are child labor laws important? So the case is about soot wart called chimney sweeps cancer that was prevalent in male toddlers. So I think I took the gruesome pictures out of here, but so how did this come about? So this physician, Percival Pott, noticed that these toddlers would come in with these ailments, and this isn't anatomy class, but half of you have a scrotum, the other half does not, and I'm assuming what a scrotum looks like, it's wrinkly. And so these toddlers would go up into these chimneys, it's hot, they'd get sweaty, the soot would get on their skin into the sweat and it would collect on their scrotum. And so they would basically develop testicular cancer. And the reason for that, I'll show you on the next slide, mechanistically, how does that happen? But he was the first one to make the connection between these toddlers, their job, and now they have this disease. So as I said, when you start adding more of these rings together, the energy gap between the highest occupied and lowest unoccupied orbitals becomes lower. The double bonds will add things a lot easier. So they'll do these addition reactions to both carbons. And based on the structure of these PAHs, since they're all sp2 hybridized carbons, right? They're flat. And we know that in the DNA double helix, there's this laddering, right? You have these base pairs. Those aromatic compounds will insert due to non-covalent interactions. And then basically a nucleophile from each chain of that DNA will connect that molecule. So if the DNA is linked, then it can't be reproduced properly. So the enzyme comes along, it sees, I need to unzipper this, but I can't. So it crashes into a wall, and that leads to all these other cellular processes. So this is ripped from a textbook. I apologize for the small structures, but so if you look right there, that nomenclature, I don't use it in this class. So here are the resonance forms. Notice how I've shifted the double bonds around. A lot of textbooks will draw that as just a circle in there. That means an aromatic compound. So instead of undergoing substitution, what you see here is an epoxidation of a double bond, and that's the addition of a CO bond to each carbon. And so we know that epoxides are pretty reactive. So they'll open up. They can form diols. And so essentially what is happening is your liver is taking this foreign substance, it's oxidizing it to make it more polar so that when it hits your kidneys, it's water soluble. So that'll happen a couple different times, and then you notice here you get this carbocation intermediate, and then you have this DNA base that's going to form a bond with it. So this is one strand, then you have the other strand. That'll form a bond there. And now it's like, see these enzymes, when they copy DNA, they like unzipper it and then copy it. But if it was stuck here, it can't keep going. And so those things lead to cancer. Any questions? Yeah.
I don't understand the simple thing, stuffing and dilution. Can you explain that a bit again?
So since DNA is a double helix, in each sort of side of that ladder is a strand. So each side has a heterocyclic base that points in, and they hydrogen bond to one another. So you get these rungs. Since this molecule is sp2 hybridized for every carbon, it's flat. So it's attracted to those rungs through non-covalent interactions or stacking. And then once it's in there, these nitrogen bases on each side will covalently bond to it. And so now when enzymes come to replicate that DNA, what they do is they unzipper it and copy each strand separately, and then it sort of comes back together. If it hits a stop, then the enzyme can't go any further. And so the DNA isn't replicated with fidelity.
So it disrupts the hydrogen bonding between the two strands? Like that's where it goes into?
Yeah, in a sense. So those were PAHs, but what about heterocycles with oxygen, nitrogen, or other elements? So we can have 5-membered heterocycles with nitrogen, oxygen, and then the elements you see are just going down the group. So nitrogen, phosphorus, arsenic. Yes, arsenic, I think. Oxygen, sulfur, selenium. So notice here we have 3 bonds to nitrogen, so that has 1 lone pair. And then I'm going to write it a certain way that'll help us a little bit later. But so oxygen has 2. So when I write that 1 inside the ring, that helps us understand it's aromatic. You can have 6-membered nitrogen heterocycles, so pyridine, quinoline, isoquinoline. You can march that heteroatom around the ring. So I think at the end of today's lecture, we're going to talk about these two a little bit in depth. Just as a question to you now to think about, what do you think the hybridization of that nitrogen is? What does it look like originally? It looks sp3. And then for pyridine, what does that look like? So it turns out they're both sp2 hybridized. And the take-home message of that is, as part of the definition of aromaticity, all of the atoms in the system must be sp2 hybridized. Just as we saw with conjugation, you're adding these alkenes. The carbons of the alkenes are sp2 hybridized. So if perol is aromatic, that means the nitrogen in perol must be sp2 hybridized. To further sort of confound this issue, the lone electron pair that I've drawn for each, even though nitrogen's sp2 in both cases, the lone pair resides in different orbitals in those two compounds. Any questions? So what does it mean to be aromatic in terms of a more chemical description of this? We're going to use Huckel's rule. And so really that basically boils down to this. You have all this other criteria, but you need to count the electrons. It has to obey 4n plus 2 pi electrons. So n can start from 0. So 0, 1, 2, 3. So it has to be a whole number integer. So as I said, visually what you're looking for is a ring that has conjugation. So as part of that, the atoms must be sp2 hybridized so that they're within that pi bond requirement. Now we're going to start counting electrons to see where they fall in that. If they do not meet 4n plus 2, then they can be other things. So non-aromatic or anti-aromatic. Another one that is, as you increase the number of n, something that can be hard to see is this requirement here, planar. So things will take on different molecular shapes as rings get bigger. And so they might not necessarily be planar, even though they have the 4n plus 2 requirement met. So cyclic, that's an easy one to see. And again, no separation of the p orbitals by sp3 hybridized atoms. So here's a chart that shows some of the classes that we'll look at where we have n, again, integers. We're plugging it into there, and that's spitting out the number of pi electrons. And then the different classes. So hydrocarbons, nitrogen or phosphorus heterocycles, oxygen or sulfur heterocycles. When n is 0, we're not going to talk about any of those molecules in this class. When we plug in n equals 1, we get 6 pi electrons, and we saw that benzene meets that requirement. We saw on the prior slide as well with the heterocycles that these will also meet the requirement. When you plug in 2, now you have 4 times 2 plus 2, that's 10. That gets you up to naphthalene. And then of nitrogen, there's these quinolines or isoquinolines. And you can see that based on what n is, you're getting a specific integer value for the number of pi electrons. So number 1, there should be no odd number of pi electrons based on what the equation is. So if you see something that says there's 13 pi electrons, you can immediately say it's not aromatic. So things that end up being 4n, so those are classified as anti-aromatic or non-aromatic. And you'll get that information from not only the Frost diagram, but where we put the electrons. So the 4n, if we start with 1, that gets us 4. That means there's 2 pi bonds. Example of that would be cyclobutadiene. So the math just kind of holds. You're just doing some multiplication, and then this tells you the number of pi bonds. So how do we draw a Frost circle? So let me tell you, through part of this exercise, even if you do meet the requirement of 4n plus 2, that's not necessarily guaranteeing to you that the molecule is aromatic. And the Frost circle is a way to help visualize that. So I'll explain what's happening here. I'm not going to read this directly, but hopefully through the explanation you understand what's happening. So we're starting with benzene. And the way that you do this is you have to point one carbon atom down, so the molecule is sort of standing on it, on a vertex. I've cheaped out. I didn't draw the circle, but what your book will do is just draw a circle around this. So that's the frost circle. And then you're going to translate where those double bonds are into these lines in the third part that correspond to the molecular orbitals. So we said there were 6 p orbitals, so we have to show 6 of these molecular orbitals. When we cut the molecule in half, that's the non-bonding line. Notice that nothing lies on that line. So we just have the bonding below and then the anti-bonding above. And then we're going to shove the 6 electrons into the bonding orbitals. So you do the lowest energy first, and then you spin pair them. So notice that within all the bonding orbitals, they're all filled and they're spin paired. So that's really what we're looking for. If you had any electrons occupying a non-bonding orbital or occupying an anti-bonding orbital, you can say that the compound at that point is not aromatic. Any questions? Yep.
What would a molecule look like if it were only non-bonding?
The first example we look at will address that. And I'll tell you right now where this sort of breaks down for my own understanding and for me teaching it to you is when you get to a ring with an odd number of atoms, because you're not going to have this nice symmetry where you can chop it right in the middle and you get an equal number, above and below, that sort of thing. So is cyclobutadiene aromatic? What? So it has to obey that with the pi electrons. So we see here we have 4 pi electrons. So that doesn't fit into this 4n plus 2. So n must be an integer. So it's, just looking at it, it sort of obeys some of the requirements. It's planar. All the carbons are sp2, it's flat, there's no break by an sp3 hybridized atom. But then as we'll see, the electron count does not match the 4n plus 2. And then when we look at the frost circle, we'll see that it doesn't fit with that either. So there's the cyclobutadiene, and I'm going to tilt it. So we're showing 4 p orbitals. So we have to show 4 molecular orbitals. And now when we slice this one, you'll see that along that line are going to be the non-bonding orbitals. So I'll just say NBO, non-bonding orbitals. So which of the following correctly categorizes the number of each type of orbital? So we have one bonding, that gets rid of A and D, two non-bonding, so that gets rid of B, and we have one anti-bonding.
I have a question.
Yeah.
So how do we know how many we have to put on the non-bonding orbital?
When it's like an even numbered ring like this, it'll be apparent. But when it's an odd number, that's when it's a little bit more difficult. So when we look at a 5-membered ring, I'll try to explain as best I can where you're sort of putting the line. Yep.
On the previous example we had for the benzene ring, we didn't have any on the non-bonding.
Right.
How do you understand that? But it was also even number.
So based on the way this is drawn, anywhere there's a vertex, you're putting a line. And so dissecting that in half, you'll see the line runs through like a bond. It's not running into one of those vertices. So if this is our frost circle, how many electrons go in the bonding and how many go in the non-bonding and anti-bonding? So we have 4 total electrons to put in those orbitals.
The bonding is filled.
Huh? Bonding's filled, yep.
Yeah.
So we put in 1, we spin pair it. Now we go up to the next higher orbital. We have 2 electrons left. So up and up. So you have to basically put electrons into the degenerate orbitals so that each get one before you go back and spin pair them. So bonding would get 2, non-bonding 2, and anti-bonding 0. So A is the correct response. Yep.
Why would you spin the cyclobutadiene, but you wouldn't spin the other one to do the line symmetry, like the benzene?
So the definition of the frost circle is that you have to have an atom pointing down. So the benzene, just the way we draw it, it's normally like that. I mean, if I drew benzene like this,
So you have
and again, this is in your textbooks. I teach it because it's in there, but for me, the frost circle is a little bit amorphous in a sense. It's a learning tool that just helps rationalize how you can plug these electrons in. So yeah, if you looked at the benzene this way, you know, this would get to your question about non-bonding, because then those central ones would be, so those would be non-bonding orbitals now. And if you plugged electrons into that, you would see you'd end up with 2 unpaired spin electrons. So it's the way I think about the frost tool is, okay, we know it should be this way, so I'm going to design this thing that sort of fits that, and it has to be, when you go through those steps, it has to be that way or it won't work out. So is cyclopentadiene aromatic? So what's a structural clue that you can see immediately that would say it's not aromatic? Huh? So it has an sp3 hybridized carbon right there. So again, with this question of is it aromatic or not, there's a lot of things you have to consider. And if you sort of negate something immediately, then you're safe. So we're not out of the woods yet here in terms of this 5-membered ring. So look at this hydrogen atom in cyclopentane versus cyclopentadiene. Both carbon atoms are sp3 hybridized. The pKa of the CH bond in cyclopentane is 50. Cyclopentadiene, it's 16. So it's similar to that of water. Based on the alkane versus the cyclopentadiene, it's a lot more acidic, right? What is the reason for that? So, for example, what this means, say we take sodium hydride. So we have H minus, Na plus. It will abstract that. To get you this anion. So let me redraw that real quick so that we understand and kind of review things. So if I said, what was the hybridization of that carbon bearing the negative charge? Through resonance, we can delocalize that negative charge. Because we can do that, all the carbon atoms are sp2 hybridized because we're using the pi system to move that negative charge in the lone pair around. Any questions? I see some furious writing, so I'll wait a second. Yeah.
So I have a question. The one you drew at the bottom, would that be considered aromatic?
We're gonna look at that case, put it through the paces, and see if it's aromatic or not. So we know that just the regular cyclopentadiene is not aromatic due to that sp3 hybridized carbon. But now we're gonna look at this structure, the anion of cyclopentadiene. So there's the anion. And now, in my opinion, this is where the learning tool sort of breaks down. So again, we're following the vertices. So we have 5 p orbitals, 5 molecular orbitals. I think a reasonable question would be, okay, where do I draw the non-bonding line? So it's not in the middle. It's going to be slightly above. So this is your pi, this is your non-bonding line, and this is your pi star. So in terms of this question, we end up with 3 bonding, 0 non-bonding, and 2 anti-bonding. So that's D. I wish I had some magic bullet to tell you where you're going to draw that line for an odd number of atoms in the ring. But ultimately, I think you have to sort of use your intuition about the number of electrons you're starting with. So for example, the reason I stuck it there and not here is because we have 6 electrons to deal with. That's going to sort of screw us because we're going to be putting electrons in non-bonding orbitals. If we drew it down there, then we'd be putting electrons in anti-bonding orbitals. In that manipulation would not translate to the reactivity of that CH bond. So I'll just answer the next question on this slide while we're here. So we have 6 total electrons, 2 from the lone pair and then 4 from the pi bonds. So we're going to put those in the same way. Lowest energy, and then pair it. Move up. This is where we put 1 in each to begin with, and then we go back and spin pair. And using some circular logic here, because they all end up in bonding orbitals, we can say that cyclopentadiene anion is aromatic. So to explain the difference in acidity, once you deprotonate it, you're forming an aromatic compound. Now it has this sort of stabilization to it. So for this, we had so we end up with 6 in the bonding, 0 in the non-bonding, 0 in the anti-bonding. Questions? So this is yes. Now the question slide. I'm cowering in fear back here based on potential questions you'll ask me about that, which I have no good answers for yet. Yeah.
Just wanted to clarify. So if the electrons are all in the bonding orbitals, then we can consider it aromatic. And
Yep.
also if all are sp2, then also we consider it aromatic. So both of them have to be fulfilled.
Yeah, you need to meet all of those criteria.
Thank you.
So we're going to finish up here on talking about these 2 specific nitrogen-containing compounds. Because really the location of the lone pair of electrons in each, as I said, is different. And we're going to see these things, coming up through reactions we learned, and then again in Module 5 when we talk about biomolecules. And so with Module 5, it's particularly important because the molecule on the left is called pyrrole. There's a derivative of that. So this is pyrrole. So a derivative of pyrrole with a second nitrogen is called imidazole. That heterocycle is present in, does anyone know what amino acid? Histidine. And so because there's two nitrogens, two lone pairs, they're very different lone pairs, that impacts their ability to hydrogen bond. And so when we learn about proteins, which are just biopolymers of amino acids, those amino acid side chains get their function from non-covalent interactions such as hydrogen bonding. So in relation to pyrrole and pyridine, the nitrogen atoms are in their neutral bonding pattern. So they're showing 3 bonds, the lone pair. And we initially said, well, the pyrrole looks like it's sp3 hybridized. But it's not because it's in the ring with these other pi bonds. The hybridization's different. And as a consequence of that, the lone pair resides in a p orbital. Whereas in pyridine, the lone pair resides in an sp2 orbital. So pyridine as a reagent is a base. Pyrrole is not a base. That nitrogen is not basic. And to use the resonance argument, and we're saying a base, that lone pair is going to go grab a hydrogen. So pyrrole can't do that because we can delocalize the lone pair through resonance throughout the ring. So the lone pair in pyridine does not participate in resonance. So it's just hanging out there. And so if it's available to bond, it can be a good base. I think in the next module, when we talk about oxidation state 1 functional groups, how do we get nitrogen into a molecule? What are the reactions? And then once it's in there, what's its reactivity? We'll delve into this pKa, pKb argument a little bit deeper. So to polish these off, pyrrole, the lone electron pair is in a p orbital, pyridine sp2. And pyridine is more basic. Just real quick, I mentioned imidazole. So that has 2 nitrogens, right? The original pyrrole one. I'll just say pyrrole type. And then look at that nitrogen. That nitrogen is pyridine type. Because the p orbital of the nitrogen is already involved in a pi bond. So that means its lone pair is in an sp2 hybrid orbital. And so that structural feature is very important for the amino acid histidine and how that acts in peptides and proteins. So any questions before we wrap up? Yeah.
So
in this molecule, that's more basic. On Wednesday, we'll introduce the electrophilic aromatic substitution. We're going to take H, put in other functional groups, and then next week, we're going to do more than one electrophilic aromatic substitution.